Welcome to lesson 3-4, linearizing data and logarithmic graph paper. So the objective of this lesson is given a set of data that does not allow a linear pattern, so this is not having a linear pattern anymore, okay? First, we transform the data using logarithms and use linear regression on the transformed data. Second, plot the data on the log-log graph paper or similog graph paper. Okay, so let's start with properties. And we have linearizing exponential and power functions. So for exponential functions, and I thought we discussed this somewhere in lesson 2 about the logarithmic functions, right? So in here, for exponential functions, if y is equal to abx, then log y equals log a plus x log b. In other words, we create a transformed, what do you call this? A transformed data using logarithms. So in other words, if your y is equal to abx, then transforming log for both of the terms from the left and from the right, we will have something like this. Okay? And following the property of the logarithm, then our transform equation will then be log of, this is product rule, and for product rule we have to separate, and this is a power rule also, so we have log a plus b or x log b, right? This is a power rule. When we have log bx, that's actually equal to x log b. So therefore, that is the most decent explanation for this transform equation. Okay, and now we have what do you call a linear data, which is in terms of course of log, and we are going to plot this data on a similog or a log-log graph paper. Now for power functions, remember that a power function has this form y is equal to axb. Now therefore, in transforming that into a log, so we have log y is equal to log a x b. Again, this is a power logarithm for this part. So we will have log y equals log of a plus log x b, and this is equal to log a plus b log x. So in verbal explanation for exponential functions, if y is an exponential function of x, then log y is a linear function of x. You get it? Yes, we do, because we have, okay, this is b, I'm sorry. We have a linear function of x now, okay? Because log of a is constant and log of b is another coefficient, which is also numerical in value. And for power functions, verbally, if y is a power function of x, then log y is a linear function of log x. Remember, look at this. This is log of x. Okay, this is log of x. So we have a linear function of log of x. Now to better show you an illustration for linearizing data, we go first to the linearizing of exponential function data. Consider an exponential function such as y is equal to 20 times 1.45x. So this is times 1.45x. This is actually x. Okay? Transform this equation by taking the logarithm of both sides. So how do we transform it? Okay, we begin with y is equal to 20 times 1.45x. So transforming this as log, we have log y is equal to log of 20 times 1.45x. So in other words, this, okay, this is log y. I'm sorry about that. So log y, and then we will have log y is equal to log of 20 plus x log of 1.45. So the log of y is a linear function of our x. Now let us see the sketch. So this is the sketch of our exponential function. Y is equal to 20 times 1.45x. Okay? So sketching it, we have, let's say, like 500 here, and this is around 1000. Okay? This is like 2468, 6, 8, 10, like that. Okay. Now we can see that the curve, if you make a table for this one, then we will have a curve which is equal to this. Okay? Okay, let me make something of, actually it's here, right? Because it wouldn't touch your x-axis because this is an exponential function. So it would be something like this. Okay, so something like that. Okay, now if we are to get the linear function of the log of x, then we should create a table for this function. Okay. So let's say my domain is from 0 to 10 this time. Okay, so from 0 to 10. Then I will have a graph which is actually, so if this is my 1, 2, 3, and so on, this is your uh, y-axis and this is the x-axis. Okay, then we will have a graph which is straight. So our graph would be something like this. Okay? If you are, if you want to prove this, then we could make a table. Okay? We can make a table from 0 to 10 and get our y. So let's say we could use this space here. So let's say my x is 0 to 10 and my y is 0. So if my x is 0, 1, 2, 3, 4, let's say up to 5 for the meantime, okay? Because the table won't fit all of the values for x from 0 to 10. And then we are going to get the graph of our log y. This is our log y. Okay, this is our y. Okay? So our log y would be, for log of 20, log 20 plus, if our x is 0, so that would be 1.30 approximately. Okay, if our x is 1, then that's log 20 plus 1 log 1.45. That's approximately 1.46. If my x is 2, then that's 1.6. 6 to 4. If my x is 3, then 1.785. Note that the increase in the exponential function, or I mean the increase in log y, I'm sorry, this is log y, is small, okay? So if my x is 4, then I would have 1.947. And if my x is 5, that's 2.108, okay? And then plotting this on a y and x axis, actually a log y and a log x axis, because we're dealing with log values here. So this is log x and this is log y, okay? I mean this is x and this is log y. So this is what we get. Okay, when we transform the data for a log of y, then we get a linear function of uh, of x for log y. Okay, now let's go to another linearizing. So linearizing power function data. What we're trying to say here is that these nonlinear data functions, including the power functions and the exponential functions, they are not linear in the standard form y is equal to something. So example for exponential, y is equal to ab raised to x. So the graph of that is not linear but an exponential curve. If we are going to take the logarithm of this exponential function, then we will get linear data, which is in log y. Okay, now the same is true for linearizing power function data. So consider an example, which is an exponential function, such as y is equal to, this is not exponential function, this is power function. So there was actually some mistake in calling it. So this is power function, okay? So our power function is y equals 800x raised to negative 1/3, or negative 1.3. Okay, transform this equation by taking the logarithm of both sides. So I think we have to begin with that. So log y, following here, okay, we have log y equals log of 800 x negative 1.3, and this will be equal to, this is product rule, this is power rule, so we will have log of 800 plus negative 1.3 log of x, right? So in the real sense of the word, power function with respect to x and y axis. So we have a power function here, and in this value we have log y, and we have log x. Okay? So if we get the power function, the sketch of the curve of this function will be something like this. Of course, we have asymptote on the y-axis and also on the x-axis. Do we have an asymptote there? Yes, we do. This is like a curve. I mean, it's like a hyperbolic function. Okay? So if this is our y is equal to 800x raised to negative 1.3, then getting the log of this function, would give us a linear function which in terms of log x, okay? And that value, we're going to graph it. That value would be something like from here going to here, something like that, okay? Okay, let's have another one, so like that, okay? So this is a linear function of the log x. This is our power function. And this is the linear function with respect to uh, y of log x. Okay, so this is the sketch. So let us now investigate a log-log graph for the power function. So generally for power functions, we will use the log-log graph paper. This is a log-log graph paper. Okay? And we are going to use this for power functions. Okay? So consider our function as y is equal to 800x negative 1.3. So considering this is our x and this is our y, then we could actually put it in a log-log paper. And this is also, what do you call this? A log-log graph paper. So if our x is 1, we're going to get from 1 to 100. So let's see, 1, 2, 1, 2, and then 5 here. Okay, 1, 2, 5, and 10, 20, 30, 40, 50, 60, 70, 80, 90, up to 100. Then the value for our y is equal to 800 something. Okay, and this will be 324.9. Well, you could verify it by putting your 1 here, and that would be 800 point something. Okay, 98.7, 40.0, and then 16.2, 9.6, 6.6, 4.9, 3.9, 3.1, 2.6, 2.3, and finally 2.0, something like that. Okay, now to plot this here on the log-log graph paper, so we would begin with 1 and 800, so somewhere here. Okay, next we will have 2 and 324.9. So where is 324.9? Somewhere, where are you? This is 300. Okay, somewhere here. Okay, next we have 5 and 98.7. So 5, 98.7. Where is that? 598.7. So somewhere here. Okay, 10 and 40. So 10 and 40. Where is 40? Here. Okay. Next is 20 and 16.2. 20 and 16.2. So somewhere here. Okay. And then what else? 39.6. And then finally 102. So 102. It's somewhere here. Okay. Let's just draw a straight line from this period going to this point. Okay, from this point going to that point. So we will have this graph. Okay, so notice that some of the points here are not actually lying on the point. So anyway, if we're going to, let's make it a little bit of smaller, I mean thinner. Okay, so something like that. Okay, and then we are to erase those points there. So these are our points. Okay, 10 here, 20. 20 is 16.2 so somewhere. And then we have this, 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 this. Okay, so we plotted all of the points for a log-log graph paper for a power function. So note that we have a straight line. Okay, for when we graph the power function 800x negative 1.3 on a log-log graph paper. Now let's take a look at the next example. Okay, now for an add multiply similar graph paper, and this is for exponential functions, then we will get x from 1, or we could start it from 0 actually. So 0, that was too thick. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say up to 10. Okay, so if our x is 0, then that would be 20 times 1.45 raised to 0. That's equal to 20. So this is 20. If it's 1, that would be, if x is 1, that would be 29. If x is 2, that would be 42.05. If x is 3, then we have 60.9725. If x is 4, we will have 88.4101. If x is 5, we will have 128.1946. If x is 6, we have 185.8822. If x is 7, then we will have 269.529. If x is 8, then we will have 390.818 or 817. I'm sorry. If x is 9, then we will have 566.685. And then if x is 10, then we will have 821.6938. Okay? So how do we graph this type of function? Okay, of course we have to start from 10. So this is 10. On the opposite, this is 0. 1, 1, 2, 3, 4, 5. 1, 7, 8, 9, 10. So this is 15. And this is 10. And then we go to 20. And then we go 50. And then we go to 100. And then we go to 200. And then we go to 500 here. And then we go to 1000. And then we go to 2000 here. And then 5000. And so on and so forth. Okay. So now we're going to connect all of the points. So our first point is, what's our first point? 0, 20. So it's here. And then next we have 129. So there's 129, something here. And the last is 10, 821. So where's 10, 821? 821. Somewhere. Okay, that's so small. Okay, let's do it here. Okay, and then I'll just connect them. Okay, so connecting them gives me this value. Okay, so these are point, 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 point. Okay, so as you can see, this is a linear function of the log of x for an add multiply simulog graph paper. Okay, so we have this paper. This is our x, of course. And this would be our y-axis. And this is our y is equal to 20 times 1.45 x. Okay? So this is the add multiply simulog graph paper for an exponential function. Okay? Now how about for multiply add simulog graph paper? We could use this for a log function of x. Okay, so y is a function of log x. So in this case, well, we would start with 1, the same as the first one. So okay, so this is my table. My table would be for x 1, 2, 5, 10, 20, 50, 100, 200, 500, 1000. Now, you may ask, why are the x like this? Why are the y like this? Now, this is the scaling for a semilog graph paper for multiply add. And for the previous one, which is add multiply, this is the scaling. Not that you have this scales for the horizontal axis, okay, but for the vertical axis you have uniform scaling. Okay, but for multiply add similar graph paper you have scaling for the logarithmic scaling for the vertical and normal scaling for the horizontal. Now in this case we have this axis, and we will substitute this axis to the equation y equals 14 minus 4 log x. So first we have when our x is 1, so 14 minus 4 log of 1 this will be 14. If our x is 2, then that's 12.79 something. Okay, continuous. So if our x is 5, that will be 11.20 continuous. If x is 10, that would be 10 also. If our x is 20, then that would be 8.79. If x is 50, so you can see that the y goes down, right? It's decreasing. 7.20. If x is 100, then this is 6. If x is 200, then x is 4.79. If x is 500, this is 3.20. If x is 1000, then this is 2. Now it's time to plot all of the graphs. So I would start with 1000, which is 2. So 1000 is 2. Have let me say it's here. Okay. Okay. You know, I just broke this thing here. There should be 5 and then 10 here, but because of we lack this space here, so I'm going to have a broken graphical illustration here. Okay, so it's like that. Okay, and then my 1 is 14. So it would be here. Okay, that's so small. Should be here. And then connecting the 2 points together, well, that's the technique that you could use when graphing to avoid inaccuracy with the other points. Okay, and it should be a straight line. So this is the graph for our function y equals 14 minus 4 log x using a multiply add similog paper. Okay, if it's 500, it's here. It's 200, it's here. 100, it's here. 50, it's here. 20, it's here. 10 would be here. 5 would be here. 2 would be here. So note that this is a linear, it's a straight line for a multiply add similog paper. Okay? And if we are to continue this, then this will go okay, that was like this. Okay? So in summary, definitions of graph paper types. For arithmetic graph paper, these are ordinary graph papers. They have linear scales on both axes. Okay, these are the graphing paper that we normally use in school. And the math paper, if you have a math notebook, this is the math graph paper that we have. The scales are uniform on both axes. While we have a log-log graph paper, which has logarithmic scales on both axes. So the log-log graph paper is like this. Okay, it has scales. Note that for both axes, for x-axis, this is our x-axis. Why did I forget to label it? So this is our x-axis, and this is for our y-axis. Okay, so they have scales, they have logarithmic scales on both axes, while for the add multiply similar graph paper, it has a logarithmic scale on the vertical axis only. So now here on the vertical axis we have logarithmic scales, but on the x-axis we have normal scales. And lastly, the multiply add similar graph paper has a logarithmic scale on the scales on the horizontal axis only. So note that only on the horizontal axis. Okay, so these are types of graph papers, and on the succeeding videos we are to solve some problem sets related to this lesson. Okay, so thank you for watching.